I'm here to talk about how we can scale up crowdsourcing for the collection of large databases by an order of magnitude speed up. So as the previous speaker, Edward, just established, hundreds of thousands of microtasks are launched every single day online. And microtasks are a very common type of tasks that are launched in crowdsourcing platforms. However, the techniques that people have been developing so far are not speeding up and lowering the cost of labeling the amount of volume of data that we're producing every single day. Most people have been working on the trade-off between speed and precision in terms of collecting large data sets. But when I want to collect my data set, I want both speed as well as precision. I want to be able to collect my data set really fast, and I also want to have a high precision. So let's start by analyzing one of the most common type of microtasks, which is the binary annotation task. An example of a task like this might look something like what you have on the right. We present workers with an image, and we ask them if this is an image of a man riding a motorcycle. And they reply by saying yes or no. This is a common interface for how a worker might do this task. They would look at an image and click yes or no, click on the next image, and continue. Even with keyboard shortcuts, it takes workers about 1.7 seconds per image. So let's put that number in context. My current research at Stanford requires me to annotate 100 million images with 50 annotations each. At 1.7 seconds, that amounts to about 2 million hours of work. And my advisor at Stanford tells me that not even Stanford can allocate $14 million just for my project. So wouldn't it be nice if we could get workers to go faster, maybe even at that speed? And that's what this paper is about. To push workers to do tasks at this speed and achieve an order of magnitude reduction in cost. So the reason workers work slowly on crowdsourcing platforms is because they're worried about getting punished. When they make an error, requesters reject their work. When their work gets rejected, their approval ratings go down, and they find it harder to find new work. This leads to crowd workers doing very slow and deliberate work. But what we want is to allow crowd workers to go faster, to even make errors. And in fact, using our interface, we encourage them to make errors. So what we need now is to be able to build a design that can tolerate the errors that workers will be making. We take inspiration from RSVP, which was developed in the 70s, which rapidly shows images to workers and asks them to respond whenever they see a positive stimuli. So a worker might see the first image, then the next one, and so forth, until they finally see an image of a man riding a motorcycle. And when they see this image, they would react by pressing the space bar. So let's see what this looks like in action. First, let's go back to the traditional time it takes a worker to do this task, which is 1.7 seconds. I'm going to show you all images at that speed, 1.7 seconds, and ask all of you to clap whenever you see a man riding a motorcycle. Are you all ready? Okay. You guys are really good at this. So now let's see if we can go just a little bit faster. Okay, let's do this again. Are you ready? That was pretty good. Now let's see how far we can push you. This is the last time, I promise. Ready? It's pretty good. So what you just saw was that these claps are delayed and often extremely noisy. But there's some amount of signal there, enough for us to build models that are robust to these errors. So the next thing we tried to do was figure out what the distribution of delays in workers look like. So given a stream of images that a worker might see, we asked them to react whenever they saw a man riding a motorcycle. In this case, it's the second image in the row. And let's say the first worker comes in and reacts after the next 3 images have gone by. We asked another worker, and that worker is a little faster and reacts earlier. As we keep asking more and more workers to do this, we started noticing that we got an X-Gaussian distribution, which is in tune with literature in psychology because they use an X-Gaussian distribution to model reaction times for workers. For simplicity, in our paper, we show that for practical purposes, a simple Gaussian is enough to model worker delays. We found that on average, crowd workers on Amazon's Mechanical Turk were delayed by about 379 milliseconds with a standard deviation of 92 milliseconds. So now that we have a way of modeling workers' delays, let's see how we can use this in a workflow and actually do binary classification. So again, we have the same setting. A worker sees these images and is asked to react whenever they see a man riding a motorcycle. So let's say the worker reacts here. And we know that they're probably delayed by about 379 milliseconds. We can now calculate the posterior probability of what they meant to actually react on. As you can see, this worker is too slow, and our model is incorrect and points at this cute red panda as the image of a man riding a motorcycle. What we do next is we take the images that the worker sees, and we shuffle them around. We change them into a completely random order. So now that cute panda is in the front, and the man riding a motorcycle is the 4th image in the list. We send this new ordering to worker 2, who then reacts to the positive stimuli. And again, we know that they're also probably delayed by about 379 milliseconds. And again, we calculate what they meant to click on. As you can see, this model is not doing so well and still thinks that that horse is now a man riding a motorcycle. But when you look at all of these workers' results together and sum up their log probabilities, you can actually start extracting out what people meant to click on. And that's it. By randomizing task ordering, by shuffling the images around, and by asking multiple workers to do our task, we can actually perform binary classification. So more concretely, given a set of images, I, each worker gives us a set of reactions, which we denote by C, and our goal is to measure the probability of an image being positive, given these set of clicks. We make the assumption that every single reaction that the worker makes is completely independent. This means that when you react, you're reacting to one very particular positive image, and not 2 or 3. And by asking multiple workers, we can sum up their probabilities, log probabilities, and actually figure out what the right positive images are. So that's what we have in our paper. We have an interface inspired by RSVP, a Gaussian model, and a workflow. And together, we're able to do binary classification. So now let's see if we can evaluate how well this workflow actually performs. So we're going to look at 3 studies that we do. The first one, obviously, is binary annotation tasks for images. So the control approach of doing this is usually majority voting, where we ask 3 workers to annotate yes and no on any given image. And we've already shown that each person takes about 1.7 seconds to do this task. The total time per image is 5.1 seconds if 3 people were to do this task. Now, using our interface, we've shown that we can get the same precision when we do binary annotation by asking 5 people. But each of these 5 people are now seeing the image for only 100 milliseconds. So in total, the time per image is about a half a second. And when you compare 5 seconds with half a second, that's an order of magnitude speed up of 10x. So we showed images at 100 milliseconds. We randomized a task order, and we showed it to 5 workers. And each task stream had about 100 images. We eliminated workers who continuously reacted just to try to game the system. And we injected gold standard positive and negative images and used that to figure out which workers were giving us good work and which workers were not. The first thing we looked at was seeing if we can detect very simple concepts like dog, or cats, or horses, things that only needed us to perceive a particular object category. And we found that our approach achieved the same precision as well as recall. The next step was to go and try to see if we can detect harder concepts, things like man riding a motorcycle, where you'd have to recognize both the man and the motorcycle, and also understand the interaction of the man riding the motorcycle. Here we found that our precision stayed the same, but our recall dropped a little bit to 0.84. And finally, we looked at even harder concepts, things like eating breakfast, where you'd have to understand the action eating and also recognize what constitutes a breakfast meal. Again, we showed that precision stayed the same, but recall dropped a little further, and now we have 0.74. But when you actually look at the speed up achieved for all of these tasks, it's an order of magnitude speed up in terms of data collection. And just like Carrie, we used NASA's task load index to figure out if workers thought that the task was had a more workload than the previous conventional approach. The NASA TLX measures perceived workload of a worker between 0 and 100. We found that the control condition had an index of 58.5, whereas ours had 62.4. And we found that the increase was not significant. We did, however, notice that the standard deviation of ours was a little larger than the control condition. But that can be attributed to the fact that workers were not used to working on RSVP-style tasks on AMT. So now that we've seen how this works, let's see if we can target recall. How do we get that to get better? So something we realized is that we can increase recall at the cost of speed up. So instead of asking workers to do the task at 100 milliseconds, we can ask them to do it at 200 milliseconds, and we saw that recall went up. This meant that people had more time to determine if they were looking at a positive stimuli, and they had enough time to make a decision on whether if they should react to it. Another way of increasing recall is to hire more workers. Instead of asking 5 people to do the task, you ask 10 people to do the task. Of course, for all of these things, your speed up decreases by half, so now you only have a 5x increase in speed up, but your recall is back to what it used to be compared to the control condition. So depending on whether you care about recall or not, you might want to use these approaches. So the second thing we wanted to take a look at was moving away from images and seeing if we can generalize our technique to non-image binary annotation tasks. The first thing we looked at was sentiment analysis of tweets. We showed people tweets at about a quarter of a second, and they reacted whenever they saw a positive tweet. And because tweets are short, people can actually read this and do it really quickly. Similarly, we asked people to react whenever they saw a synonym. For example, we'd give them the word wide and ask them to react whenever they saw something that meant the same thing. In this case, they would react to broad and not to hushing, crunch, or short. And we found that workers were able to do this at 0.6 seconds per word. And finally, we really wanted to stretch this. We gave workers long articles of around 105 words and asked them to classify them into a category that we were interested in. In this case, we were looking for articles about housing. So whenever they saw an article about housing, they would react. Now, traditionally, workers took about 14 seconds. That's because they would read the entire article and try to figure out if it actually belonged to that category. But all you really need to do is pick out these key words and use that to determine if you're actually looking at housing or not. And using our interface, that's what workers learned to do. And again, we achieved an order of magnitude speed up for both sentiment analysis as well as topic detection. We got a 6x increase in word similarity. And finally, we wanted to go away from binary classification tasks and show how we can use this for multi-class classification. So what that looks like is not just classifying images as being dog or not dog, but it means classifying images as people, dog, horses, cat, etc. And we did that through a series of binary annotation tasks using our interface, and we were able to annotate a data set of 1,000 images, and we were able to do it using our interface for under $20, whereas the control method cost about $170. And that's an 8x increase in speed up for multi-class classification. However, there are some things I would like to discuss about our approach. We wanted to see if workers were able to pick out successive positive stimuli. So if you had multiple images of a man riding a motorcycle, would workers still be able to get it? And we found that at 200 milliseconds, yes, workers were still able to catch every single one of them. Next, we wanted to see what would happen if majority of our images were positive. What if more than 50% of our images were of man riding a motorcycle? And again, we found that we were actually able to collect all of them. What we did realize, though, is that when we increased the speed from 200 milliseconds to 100 milliseconds, that workers started incurring what we call attention blink. It's an established term in psychology research, and they can't detect successive, and I see people nodding their heads, that's great. They can't detect successive positive stimuli. So before I end, I did want to leave myself some time to tell you that the code for all of this is online, available for free. And I would like everyone to go check out the demo right now, and let's actually try to do this task, right? So it's hci.st/demo. So let me do it here while everyone else gets set up as well. So that's the URL. If you have a cell phone, you can use your cell phone too. Okay. So currently, the status is we have a lot of images on the right of man riding a motorcycle and others. And our aim is to collect all the man riding a motorcycle images. Currently, the precision is 0.2 because all the scores are equally divided between all the images, and our model has no idea which ones are correct and which ones aren't. The moment you press start, our workflow will give you a set of 100 images, and your job is to react by either pressing the space bar or just tapping your phone after you press space, after you started it. So I'm going to do it here. I encourage anyone who has their laptops or cell phones to also try it. Okay, so let's see how I did. So with just one run, I was able to get a 0.75 increase. So what it looked like before was the curve down there, and after my current run, it goes up to 0.75. So has anyone gotten a better score than me? I'm gonna take that as a no. I've been practicing a lot. So with that, I am ready to take questions.
Microsoft Research. Great work. I wonder if you have tried with the similarity of the distractor images. So for example, instead of having, well, you have the man on a motorcycle, but if some of your distractor images would have a woman on a motorcycle or a man on a motorcycle but not riding it.
Yes.
And also the same for the text. So you might have articles where it has homes and realtors, but it has nothing to do with housing.
That's actually a great question, and I think I have a slide for this as well. So unfortunately, you can't do this for fine-grained detection. When you have things which are very, very similar, the only way to increase recall is to actually, so this is a recall problem, and not precision. And the only way to increase it is what I mentioned earlier, by slowing down the task significantly. Yeah.
Hey, Nikki Couture, CMU. Really, really fun stuff. So you probably have a slide for this as well, but it seems like this is parameterized around the number of tokens or labels that you're looking for, right? So if something could be, if you have 10 words and it could be any of 10,000 things, you need to do 10,000 binary passes through it, right?
Right.
I'd probably just want to, get a few people that, people have like a million words of like the English language in their heads, right? So do you have any sense of like where the trade-off is when, the number of tokens versus the amount of stuff that you want to be looking for?
So you're specifically asking about multi-class classification, right? Where you have multiple things that you want to tokenize and you're going through multiple passes through your data.
Right, where the multi-class could be the
Right.
million words of the English.
So the nice thing about most of the sets in the world, like words in the English language or images or object categories, is that they follow a Zipfian distribution, which means there are very common things in the head of the tail, and the head of the distribution, and there's a long tail of very infrequent objects. So yes, we do answer this in the paper, and I don't have a slide for this. But what we do is we pick the most common element that we think is in the distribution, and we can do that using some sort of prior that we have about either the English language or the kinds of objects that occur in images, and we tackle that first. So we get all of those images, and the next pass, those images are gone. So we have significantly fewer images. And because of that Zipfian distribution, we eliminate an exponential amount of images at every single pass. And the number you saw earlier with the 8x is using that approach.
Hi, Joel Chan, CMU. So it's really cool that you were able to show the NASA cognitive load thing, no difference between the conditions. I'm assuming that's after one exposure to the task. I wonder, so I want to check my assumption. Were there workers that completed multiple rounds of this, and is there a sense of any cumulative cost that's hidden? Maybe so the first time doing it's not so bad. After 10 times doing it, you kind of like start to get hits and error rates and so on. And kind of related to that, did you get any qualitative feedback from the workers?
Right, so those are amazing questions. So yes, we did have workers do multiple tasks. In fact, I think we had workers do about 100. I think that was the most that a worker did was about 100 of these. And we did not get any qualitative feedback. We did ask them for comments if they had any, but we never got anything back. We did not see any decrease in quality, however. And that could also be attributed to our gold standard injections that we were doing. So because of the positive and negatives, our model could pick out exactly which workers were doing good work and which ones weren't. So we were automatically rejecting and approving workers. But I did not see any decrease over time as workers did more tasks.
Good. Maybe we can take more questions offline.
Thank you.